So the problems we're going to be doing today involve not mutually exclusive events. So the last video I talked about mutually exclusive events. Those are events that cannot occur at the same time. Well, not mutually exclusive events, or we can call them combined events, are events that can happen at the same time. So these are events that can happen at the same time. So say I'm rolling a die. I'm interested in the event when I roll a prime number and an even number. Well, those two events are not mutually exclusive because, for example, we could roll a 2, and 2 is both prime and it's an even number. So these two events are happening at the same time. We can also think of this situation in a Venn diagram. So remember, when I drew a Venn diagram for mutually exclusive events, those two events never intersected. Now, if they are not mutually exclusive, they can happen at the same time. There definitely can be, or there has to be, an intersection of those two events. So if we're thinking about rolling a die and getting a prime number or an even number, if I drew a Venn diagram about that, here's all the prime numbers, prime, and all the even numbers. So if I roll a die, I could get a 1, that's neither prime nor even. I could roll a 2, that's both prime and even. I could roll a 3, which is prime. 4 is an even number. 5 is a prime number, but not an even number. 6 is even, but it's not prime. You can definitely see the intersection of those two events happening, so they're not mutually exclusive. So there's a formula for finding the probability of combined events. We say the probability of A or B, so this is for not mutually exclusive events, is equal to the probability of A plus the probability of B minus the probability of A and B occurring. And the probability of A and B cannot equal 0. Otherwise, it's a mutually exclusive event. So this notation right here, this right here means or, this means and. So if we want to find the probability of A or B happening, we're going to take the probability of A plus the probability of B minus the probability of A and B occurring. This is a formula that you don't have to have memorized. It's given to you on the formula sheet. We're just going to get familiar with it, and you might have it memorized by the end of this probability unit because you'll be using it so much, but I just wanted you to know that you don't have to memorize it. So some example problems. So say we wanted to find each probability when drawing from a standard 52 card deck. I wanted to find the probability of drawing a black card or a 5. So we want to find the probability of drawing a black card or a 5. Well, first of all, we need to think, is this mutually exclusive or is it not mutually exclusive? Well, if you are familiar with a 52 card deck, we have black cards and we have red cards, right? In the total deck there are 4 cards that are 5s. And 2 of those are black and 2 of those 5s are red. So these are not mutually exclusive because they can happen at the same time. We can have a black card that's a 5. So what we're going to do is we're going to find the probability of getting a black or a 5. I did B for black. That's going to equal the probability of getting a black plus the probability of getting a 5 minus the probability of getting a B and a 5. So we need to find the probability of each of these. Well, if we're just drawing one card from the deck, then our denominator is going to be 52. There's 52 possibilities, right, in a 52 card deck. So that goes in the denominator, and so then we want to know how many black cards in a deck. Well, half of the cards are black, so that would be 26. Satisfy that event. So 26 cards out of 52 cards are black. How many 5s are there? There are only 4 5s in a 52 card deck. And then we're going to subtract the probability of getting a black and a 5. So there are 2 cards in a deck that are both black and 5. So then we have to do 26 plus 4 minus 2. So we have 28 over 52. And that reduces to 7/13. So the probability of getting a black card or a 5 is 7/13, or 7 out of 13. So the next problem asks, what's the probability of drawing a black card and a 5? Well, getting a black and a 5. That's funny, the order I put those questions in, because isn't that answer right here? We already found the probability of getting a black and a 5, and that's right here, 2 out of 52. There's only 2 cards in a deck of 52 that are black and 5s. So that simplifies to 1 out of 26, or 1/26. So our next problem, we're going to find the probability of rolling a fair 6-sided die and have a prime number or an even number show. So this is my original example when I was explaining the difference between mutually exclusive and not mutually exclusive. So let's actually find that probability. So I want to know the probability of getting a prime. I'm just going to do P for prime, or an even. I'll put E for even. So 5/6 is the probability of rolling a prime number or an even number, which is a pretty high probability when you roll a die of getting a prime number or an even number. Okay, the last problem of this video, I wanted to show you a problem with a table. IB really likes to put data in tables, so I want you to become familiar with how to read these tables. So I have this problem where we are looking at this chart, and the chart was used to see how many Annie Wright School juniors and seniors regularly wear pants or skirts for uniform. So we have juniors that wear pants, 10 wore pants, and 32 wear skirts regularly. And then for the seniors, we have 14 that wear pants regularly and 26 that wear skirts regularly. So if a student is selected at random, we want to find the following probabilities. We want to find the probability that a student is a junior and wears pants. Actually, before we do this, we should probably find some totals here, because that's going to help a lot. I want to know how many juniors I have, and how many total girls wear pants and how many total wear skirts. I also want to know how many seniors I have and how many total students. So there are 42 juniors, 10 plus 32. There's also 40 seniors, 14 plus 26. So I asked a total of 82 students. Then 24 regularly wear pants, 10 plus 14, and 58 regularly wear skirts. Okay, so now I think we can do the problem. So if I want to know the probability that a student is a junior and wears pants, all I have to do is look at my table and my answer is right there. Right here, this number 10 is the number of students that are juniors and wear pants. Right here, 10. So that goes in my numerator. 10 goes in my numerator. So 10 students out of a total of 82 students. 10 students are juniors and wear pants, and there's a total of 82 students. So if I can simplify my probability, I definitely want to, and this can be simplified to 5 over 41. So that's the probability of a student that is a junior and wears pants. And remember, of course, you can always put these into percentages or decimals. So if I put this in percentage, then it would be using 3 significant figures, it would be 12.2%. So I have a 12.2% chance of picking a junior that wears pants. The next problem is I want to know the probability that a student is not a junior. So the probability that a student is not a junior. So I'm going to put the prime notation, and that means the student is not a junior. So I can go about this a couple ways. I can basically I can just look at the seniors, right? So there's 40 students that are not juniors. So 40 out of 82, right? You could also do 14 plus 26 over 82, but we already did 14 plus 26. We found that it was 40. So 40 out of 82 is the probability that the student is not a junior, and I'm pretty sure we can simplify that as well. We can simplify it to 20 over 41. And if we want to put it into a percentage, we would put it as 48.8% in 3 significant figures. Okay, so then for the last problem, I want to find the probability that a student wears pants or is a senior. So first of all, my question to you is, are these mutually exclusive events or not? Well, just looking at the table, we can see that there is in fact students that are seniors and wear pants, so they are not mutually exclusive events. Therefore, we need to use the formula where we take the probability that the student wears pants or is a senior. We'll take the probability the student wears pants plus the probability that the student is a senior minus the probability that the student wears pants and is a senior. So the probability that a student wears pants is 24, because that's the total of this column, 24 out of 82. The probability that a student is a senior would be this row, so 40 out of 82, minus the probability that the student is a senior. So that would be 14 out of 82. Another way to think about it is we only want to count this group once. We only want to count the probability that a student is a senior and wears pants once. And we've counted it twice. We've counted it once with the 24 when we added these columns together, or this column together, and we added 14 when we added this row together to get 40. So we only want to count these seniors that wear pants once, so we have to subtract one of those. So we're just going to do 24 plus 40 minus 14, and we get 50. So 50 out of 82, which simplifies to 25 over 41. And that's the probability that a student wears pants or is a senior.